Hello, and welcome to my talk about improving fairness in AI models on electronic health records, the case for federated learning methods. I'm Raphael Poulain, a third-year PhD student at the University of Delaware. So let me dive in a little bit into the motivations for this work. First, data availability is often a major limitation in machine learning applications in healthcare. Therefore, federated learning methods can help increase the diversity of the dataset and thus allow for fairer predictive models in healthcare predictive tasks. Second, studies investigating fairness in healthcare often only consider binary sensitive attributes. However, attributes like race, insurance type, or age are by nature non-binary. It is therefore important to develop methods that are suited for non-binary scenarios, as those can be a source of great biases. And lastly, federated learning methods investigating fairness often rely solely on the weight aggregation process, leaving the local debiasing part to the discretion of each client. However, we believe a unified debiasing technique is critical in such high-stake applications. Now let me introduce briefly how federated learning can be used in healthcare settings. So federated learning allows for multiple healthcare sites to collaboratively train a single model. And in a common federated learning paradigm, each client would train a model on their local datasets and send the trained parameters to the aggregator, to a server. The server then aggregates the parameters across each client and sends the aggregated parameters back to the clients. This process represents one round of federated learning and is usually repeated numerous times until convergence. And so this is a very particularly useful paradigm as the hospital can collaborate to train a more efficient model while staying compliant with their data privacy processes. So now that we've established how federated learning can be used and why it can alleviate fairness concerns, it is important to have meaningful metrics to quantify how fair a given model is. So while there exist many metrics to quantify fairness, those metrics are often limited to scenarios where the sensitive attribute is binary. In this paper, we use parity-based metrics and minimax group fairness in non-binary scenarios. The parity-based metrics ensure that the performance do not differ too much between each subpopulation, while the minimax group fairness focuses on improving the worst performing subpopulation. And to ensure the metrics are able to be used in non-binary scenarios, we propose to use the standard deviation. Notably, we use the true positive rate and accuracy parity standard deviation, so the TPSD and APSD, and the worst performing TPR that we note worst TPR. So in this paper, we propose a method that tackles fairness on both a client level and on a server level. So for the client level, we perform local debiasing through adversarial removal of sensitive information. And for the server level, we introduce a fair aggregation process that allocates more weight to consistently fair clients. It is also worth mentioning that our aggregation process is fairness metric agnostic, meaning that it can be optimized for virtually any desired metric. Our original model is composed of a bidirectional recurrent neural network with an attention mechanism. And to perform adversarial removal of sensitive information, we add a classifier on top of that. That classifier will be trained to predict the sensitive attribute of the patient given the representation produced by the recurrent neural network. Now, the rest of the model is trained to produce representations that do not contain sensitive information while remaining useful in downstream tasks, meaning it will not only be trained for the downstream task, but also to maximize the loss of the sensitive attribute classifier. On the server side, our aggregation process is based on Fed-average, one of the most popular federated learning algorithms. And as a matter of fact, the initial client's weight at round 0 are initialized proportionally to the client's dataset sizes, similar to what was proposed in Fed-average. Then the new client's weights depend on previous weights and the current fairness metric. Doing so allows us to reward consistently fair clients, as one fair round would not drastically increase a specific client's weight. We also introduce a hyperparameter beta to balance the importance of the fairness components. Also, it is worth noting that when beta equals 0, then the fairness component does not play any role. Therefore, the proposed method would become identical to Fed-average. To evaluate the efficacy of our method, we have created 4 distinct cohorts from 2 different datasets. We have used 2 cohorts from the Cynthia dataset to perform a mortality prediction task after inpatient visit discharge. Here, the patients are represented by the states the hospital are located in. We have two different scenarios, one with the 5 most populous states, offering a rather similar distribution amongst clients, and one with very, very different demographic distribution, the heterogeneous state scenario. And additionally, we have used the MIMIC3 dataset to perform a mortality prediction task in the ICU for 2 different cohorts. One where the patients were randomly assigned to clients, called the MIMIC3 IID, and one where the patients were assigned to clients to simulate a non-IID data distribution among clients, called the MIMIC3 non-IID. And here we can see some detailed statistics about the distribution of each client for every cohort. And for all cohorts, we have compared our proposed method to 3 baselines. No-Fed refers to the case where the clients do not collaborate and train their model independently. Fed average is, as I mentioned earlier, the most popular federated learning algorithm, and FairFed is another federated learning method developed to improve fairness, similar to our proposed method. And we can see that for most fairness metric, our proposed method performs better, as shown in the last column, while remaining close to Fed average in the second column in terms of accuracy. It is also interesting to mention that the difference between Fed average and no Fed showcases the importance of the federated learning scenario, proving the need for hospitals to collaborate, both for better accuracy and fairer models. Additionally, we have performed an experiment to evaluate the impact of the fairness budget beta on the accuracy and the fairness metrics. Here we report the results obtained on the MIMIC3 IID cohort. And as we can see, as we increase the value of beta, the accuracy steadily decreases, while the fairness metric seemed to improve at first. However, when beta reaches 2, even the fairness metrics start to worsen, which is most likely due to the fact that the method gives too much weight to certainly fair clients instead of rewarding consistency. So to conclude, the proposed method allows for healthcare sites to collaboratively train a model that mitigates fairness for scenarios where the sensitive attribute is non-binary, and also the method is by nature agnostic to the desired fairness metric. And lastly, the proposed method not only mitigates fairness as part of the aggregation process, but the FL-based algorithm implicitly helps with addressing data imbalance and increasing the data size. So this is the end of my talk. Thank you very much for listening, and I would like also to thank my co-author Farhan and my advisor, Professor Beheshti.